Okay, so we have a very long problem for example number 6. Okay, let me read this in detail. So solar radiation is incident on the glass cover of a solar collector at a rate of 700 watts per square meter. The glass absorbs 88% of the incidental radiation and has an emissivity of 90%. The entire hot water needs of a family in the summer can be met by two collectors, 1.2 meter and 1 meter wide. The two collectors are attached to each other on one side so that they appear like a single collector, 1.2 meter by 2 meter in size. Okay, that's quite interesting now. So we will only represent this as 1.2 by 2 meters for the area. The temperature of the glass cover is measured to be 35 degrees Celsius. The surrounding air is 25 degrees Celsius and the wind is blowing at 30 kilometers per hour. The effective sky temperature between the glass cover and the open space -40. So water enters the tube attached to the absorber plate at a rate of 1 kilogram per minute, assuming the back surface of the absorber plate to be heavily insulated, and only heat loss to occur through the glass cover, determine the total rate of heat loss from the collector. The collector efficiency and the ratio, which is the ratio of the amount of heat transferred to the water and the solar energy incident on the collector, and the temperature rise of the water as it flows through the collector. Okay, so to find A, no, sige, let's first define the problem properly, ano. So we have a solar collector here, no. It has the solar radiation going in through it, no. So it hits this water, no, inside this radiator, diba? This radiator, this solar collector. So this heat is converted into the temp into a higher well, it is not really converted, no? It heats the water at higher temperatures. But as you can remember, we can have a heat loss, no? Because this interacts with the surrounding. The temperature of the surrounding is different than the temperature of the surface of the plate, including the sky, no? So there is convection and radiation. So there will be some losses, no? In the solar collector. So basically, if you have this as your solar collector, as you can see here, so this is the Q added by the solar, no? Solar or the sun. And some of it will be absorbed into the inside of this plate, no? So just imagine that it will be into the inside. So this is the Q absorb, no? Imagine this is the node, this is the absorb, no? And then since the temperature of the surrounding is higher, or sorry, well, lower than this point, no? So there will be heat transfer going to the air, no? So this will be the Q loss, no? Which includes both the convective heat transfer. Actually, we don't have a dot here. So Q convective and Q radiative. So it is emitting radiation outward and also losing heat due to convection. Also, we have here a wind blowing at 30 kilometers per hour at 25 degrees Celsius. So we just want to find this Q loss first, and then we can find the efficiency. So the efficiency is basically what is the output versus the input. So the output here is the absorbed heat over the input, which is the solar, no? And then the temperature water, no? So the water will be going through for this case. It will be going this way. So cooler. Okay, we can have a cooler water here. So it will be going to this temperature at the inlet and the temperature at the outlet. So we can use MCP delta T, no, for finding the temperature rise, assuming that we know the heat absorbed. Okay, so let's begin with finding this, no. So for QCon and QRAD, QRAD is basically much simpler, no. So I hope you can still remember this. It is much simpler since everything is given here. So we will only what we will use here is only the emissivity, no, for this QRAD 0.90 and the area, no, and the temperature difference of the sky and the collector for QRAD, no. So we won't need the 88% since this is the the solar, no? So it is a different a different it has a different use, no, for our problem. But for convection, we need to first find H, no? So since HA and then change in temperature, so we need to find the coefficient, no? Convective, heat convective coefficient H. So in this case, we have a flat plate, so we will just use the flat plate, no? Consideration. So in order to do that, for flat plates, always remember that this will always use the film temperature, which is the average temperature of the surface and the free stream, no? So in this case, you have the free stream is 25, no, of the air, and you have 35. So 25 plus 35 divided by 2. So this is 60. So therefore, we should use 30. No? We should use 30. Okay. So to find, we want to first determine if this is purely laminar or mixed. No, we will not discuss the purely turbulent. No, it will be said if it is purely turbulent because most of the cases it will be either only, laminar or mixed. No, for our course. No? So you have T. Sorry. You want to find the Reynolds number first. So Reynolds number is just the velocity, and then the length, and then the viscosity, no? The kinematic viscosity. So the velocity here, 30 kilometers per hour. So you have 30 kilometers per hour. So to convert this into, we need to convert this into meter per second, no? Because the units of kinematic viscosity is in meters squared per second. So 1 over 3,600, no? Or per hour, or per second, and then you have 1,000 kilometers, no? So you have 1,000 meter over 1 kilometer. So I'll just use 1.1 over 3.6, no? Sorry guys, pero I just want to make things a bit more compact. So 1 meter per second is equal to 3.6 kilometer per hour. Yeah, I think this is pretty clear, no? And then multiply this by the length, no? So the length here of the solar collector. So which one should we use? No? Which one should we use? Which length should we use? Is it, no, it should be this direction, or should it be this direction? So the air is blowing at 30 kilometers per hour. Hmm. It should be the wideness. So it should be 2 meters. No? So the length should be 2 meters, since oftentimes the airflow should be in this direction, no? It's not really in that direction because it is oriented in this way, no? So we will just assume that this will be going into this direction, although it could be correct still that it could be in this direction, but we will just use this direction for now, no? Okay, so you multiply this by 2 meters, no? 2 meters, and then divided by the viscosity or kinematic viscosity, 1.608 times 10 to the negative 5. So meter squared per second, yan. No? So this should be in meter per second, no? Times meter, so meter squared per second. So the Reynolds number along this length, no? So you have 30 times divided by 3.6 times 2 over 1.608 10 to the negative 5. Okay, so we have this. Ayan. So, ayan. So, 1.03. 1.0365. No, I'll just use 4 significance figures. 1.306. Actually, 637 na lang, no? Times 10 to the 6. So, since this is greater than the critical Reynolds number, which is 5 raised to 10, raised to 5. So, therefore, this should be we will only use mixed, no? We will not use the turbulent unless it is otherwise specified that it's purely turbulent, no? It should be mixed. That is why what we will do is we have a longer formula for the Nusselt number. So the Nusselt number is equal to, so just check my notes here. So 0.037 Reynolds number raised to 1 half. 0.8 pala, no? Sorry, 0.8. 0.8 0.8 minus 871 and then raised to multiply by the Prandtl number. Sorry, not really that clear. Should be 1/3, no? I'm pretty sure it's 1/3. Ayan. Should be 1/3. Okay. So 1/3 for the Prandtl number. And then we know that the Nusselt number is equal to HL over K. Therefore, we can find H. So H here is K over L multiplied by the Nusselt number. Okay, so I'll just do this this H here. I'll solve this simultaneously. Just use a calculator. So we have K thermal conductivity 0.02588 over length. So length natin ay 2 meters, right? So 2 multiplied by the Nusselt number. So the Nusselt number you have 0.037. Reynolds number is 1.037 times 10. Can we do that multiply, no? 1.037 times 10 to the 6. Raised to, actually, I'm not sure if this will work. So let me use parentheses first. And then 0.8 minus 871. And then Prandtl number. So the Prandtl number is 0.7282 raised to 1/3. Yeah. Okay. So the answer of 6 octal multiply. Oh, why? Huh? So, we have too many parentheses. No? Copy this. So you have 17.84. No? So 17.84 watts per meter squared Kelvin. Okay, so now we have this. We can now solve for the convective heat loss and therefore we can find the Q loss as well. So for the Q loss, I think I'll just write this down here and then we can use another page. Okay, so HA delta T. So T PS, no? Minus T infinity. So it should be positive, no? Gawin na natin positive lagi. And then the radiative. So since they are going outward for both. And then plus the radiative, you have the emissivity, sigma, the area, and the fourth, no? Fourth power of, you have TS, no? To the fourth minus T sky, no? To the fourth, since it is emitting radiation into the sky. I think this will fit in our calculator. So let me just solve this directly. So the Q loss, so save this. So you have here the convective coefficient saved as A, and then the area. So the area here is 1.2 times 2 only. So 1.2 times 2. And then you have TS minus infinity. So 35 minus 25. Okay, plus you have the emissivity, so 0.9. And then Stefan Boltzmann constant, 0.467 raised to -8. And then times the area, so 1.2 times 2. And then multiplied by the fourth root. So this should be an absolute value, no? The surface and the sky temperatures. So let me just write this off. 35 plus 273. And then the sky, no? So the sky is -40. So -40 plus 273. to the fourth. Yeah. So the heat loss is 1169. Let me just see. Okay, we have it correct. 1169.34. So Q loss for A is 1169.33 watts. Yan. So ito na yung final answer natin. Tapos na tayo sa A. Okay na sa A. So for letter B, we want to find the collector efficiency. So for the collector efficiency, what happens is, again, so if you have your solar collector, this is the side view. No? So heat is added, no, due to radiation, solar irradiation, and then it will be absorbed within. No? So Q abs, no, within this node. Let me just, yeah, like this, and then the heat absorbed will be rejected now through this cooling water, no? Or actually it is kind of cooling water, but we want to heat the water in this case, no? So we have this temperature, yeah, entering temperature and also the exiting temperature. Although we are interested in efficiency, so in efficiency, we all know that efficiency is just how much output, no, is utilized versus the input of the system. So in this case, the output is what? No, the absorbed heat. No? So the absorbed heat is just how much of this is utilized uh, as a as a way to heat your water. No? So this will be Q absorbed, diba? Which is what? No? So we know that Q abs. No, if you do the balance, no, in this node, so we have a Q loss exiting here. So your Q abs is also equal to Q abs is also equal to the solar, no? Solar irradiation, and then minus the Q loss. No? So the difference of these two. Okay? And then divided by the input. So the input here is what is the irradiating, what is the solar radiation or irradiation. So in this case, the input here is, we have here the 700, no? And 88%. So it will absorb 88% of 700. No? So we have the absorptivity multiplied by the Q, no? I think this is in square meter, no? So I guess this will be Q times area only, no, of the irradiation. Yeah. Okay. So I think I think we're good with this. So the Q solar, how do we find the Q solar? The Q solar is also actually this is the same, no? These two are the same. Actually, I should write this as Q solar first. And then we can write this off. We know that Q solar is equal to the absorptivity, the heat flux, no, and then times the area, no. So in this case, you have 0.9, and then you have 700, and the area is 1.2 times 2. So if you check the units, this should be consistent. So we have watt per square meter, and then you have multiplied by square meter. So basically, it's just the same, no. Okay, so we have here, I think I'll solve this first. So 0.9 times 700 times 1.2 times 2. Okay. Sorry, we don't need to use the denominator. So we have 1512. Sorry, 0.88 pala. No. 0.88 to. No. Sorry. You should include the absorptivity instead of the emissivity. Ayan. So this will be 1478.4. 1478.4. So in watts, no? So 1478.4 minus the heat loss is 1169.33, and then divided by again 1478.4. So we can see the efficiency, no, the solar efficiency is okay, so yeah, 1478.4 minus 1169 0.33. What? Sorry. 1478.4. So we have 20.91, no? So 0. Actually, I'll just represent this in percent. So 20.91%, no? For the efficiency. Okay, so the heat loss is very high, no? Okay, now for the last one, how do we now find the temperature rise of the water as it flows through the collector, no? So we know that only the absorbed heat is utilized for cooling or sorry, for heating the water. Therefore, the energy in, energy out, no, scenario is included here. So basically, the heat absorbed by the solar plate collector is equal to the energy gained by the water, no. So in this case, you have the difference between these two. So Q abs, Q abs is equal to this. I just write this here. So Q abs is equal to Q solar minus Q loss. Okay. So this will be 1478.4 minus, I think I'll just write this down first. Q solar minus Q loss. And then the energy gain of the water is just MCP, no? CP delta T. Do we have a mass flow rate of the water? No? I think we have a mass flow rate here. We have 1 kilogram per meter. Water enters the tubes at 1 kilogram per meter. So this is given. CP of water is 4.1. 27, and then you have delta T. So we just want to find the delta T. So everything here is already solved, no? So delta T is equal to Q solar minus Q loss over MCP, no? So divide this by MCP. Okay. So this will be 1478.4 minus 1169.33, 1 kilogram per minute. So take note of the units, no? So this is in watts. So we have kilogram per minute, 1 kilogram per minute. So we want this to be in kilogram per second. So 1 minute, 60 seconds. And then CP is 4.187. So actually, this is in kilojoule. So 4,187 na lang, no? Joule per kilogram Kelvin. Okay, so we can cancel this. So this will become kilogram per second, right? So we can cancel this kilogram. And then we know that watts here is in joule per second. So we can cancel the second, no? And then we can cancel the joules. So it will be in Kelvin. So delta T is, I use this one. We have 1 divided by 60 multiplied by 4187. So we have 4.43. Yes, 4.43, no, approximately 4.43 degrees Kelvin. Okay, or in degrees Celsius, it could be also true, no? Or Kelvin degree if you want. So that's it for this example. That's a lot, no? Thank you guys for listening.